We're finally in a position where we can define something called modular inverses. Remember, in the real or complex numbers, you're probably used to thinking of negative exponents referring to reciprocation, like 3 to the minus first power just means 1 over 3. 8 to the minus third power just means 1 over 8 cubed, stuff like this. But for us, remember, all the definitions and theorems always assumed things were integers. So if we want to start working with negative exponents, we need to make sure things are still integers, and this interpretation is not going to work out very well. But if you think about negative exponents as developed from the ground up, it's not really defined through reciprocation. They're defined to satisfy the exponential identity x to the a times x to the b should be equal to x to the a plus b. So for example, for any number x to the first is the same thing as just x. So if this identity holds, then x to the 0 times x should be x to the 0 plus 1. Well, 0 plus 1 is just 1, and x to the first is x again. So x to the 0 times x was the same thing as x. So as long as x isn't 0, you can cancel it from both sides and get x to the 0 needs to equal 1. So it's not so much a random definition that something to the 0 is equal 1. It's so that this identity is maintained even if one of these numbers is 0. Then we can keep working with this idea. What should x to the minus first mean? Well, according to this exponential identity that we want to keep true, x to the minus first times x to the first, I should be able to add the exponents and get x to the 0. We've just seen that x to the 0 should equal 1. So x to the minus first times x to the first is equal to 1. If we're doing real number arithmetic, we can now divide by x and get x to the minus first is 1 over x. But it wasn't defined this way. It was simply a product of our assumption that the exponential rule, where the product of two exponentials is an exponential of a sum, was going to remain true. So we can extend this notion to modular arithmetic to get a notion of negative exponents without having to do any division. So we know for positive exponents, our desired exponential identity already holds. How do I know this automatically? Well, whatever x, a, and b are, assuming they're all integers, x to the a times x to the b is simply equal as integers to x to the a plus b. And if those two integers are equal, they're definitely equivalent mod n. Similarly, x to the 0 is just equal to 1 as an integer, as long as x wasn't 0 to begin with. So x to the 0 is definitely equivalent to 1 mod n. So now for negative exponents, we're going to attempt to maintain the same identity that x to the a times x to the b should be equivalent to x to the a plus b mod n. Well, if I want to include negative exponents, I should at least be able to account for negative 1. So we make the following observation. X to the minus 1 times x to the first, if this law holds, should be equivalent to x to the 0. We already know x to the 0 is equivalent to 1. So whatever x to the minus first would mean, x to the minus first times x should be equivalent to 1 mod n. We're not requiring it to equal 1 as an integer, just be equivalent to 1 modulo n, a very important distinction. So we define if a and b are integers so that the product is equivalent to 1 mod n, we're going to say that they are inverses mod n, and we're going to borrow this exponential notation and say a is equivalent to b inverse mod n, or b is equivalent to a inverse mod n. And remember, we only require the product of the two numbers to be equivalent to 1 mod n. We do not require the product to equal 1. So for example, 2 times 3 is equal to 6. In integer arithmetic, 2 times 3 is 6. However, if I'm working mod 5, 6 is equivalent to 1. So 2 times 3, while it is definitely not equal to 1, it is equivalent to 1 modulo 5. So we can write 2 inverse is equivalent to 3 mod 5, or 3 inverse is equivalent to 2 mod 5, because the product of 2 and 3 is equivalent to 1 mod 5. However, do not write 1/2 is equivalent to 3 mod 5 or 1/3 is equivalent to 2 mod 5. We're only writing integers. So don't start writing these fractions when what you really mean are modular inverses. We really want to keep separate equality versus equivalence And in equivalence, we really want to have only integers, so this fraction would be a problem, and in here, we accidentally put an equal sign rather than an equivalence. And even with an equivalence, we wouldn't want this fraction in there. So the notation is similar because the notions are similar, but it's not the same, so do try to keep it separate. And we can apply the same notions to get all of our familiar properties of exponents, even for exponents beyond the negative first. So let's suppose a and b are integers, j and k are going to be our exponents, and they can be any integers, and n is any allowable base. A to the j times a to the k is always equivalent to a to the j plus k. A times b to the j is always equivalent to a to the j times b to the j, and a to the j to the k is equivalent to a to the j times k mod n. So all of our familiar laws of exponents work just fine, provided that all of the terms I've written down even exist. And with negative exponents, there can be some issues with whether or not certain things even exist. So for example, there is no a, so that 2 times a is equivalent to 1 mod 4. Anything equivalent to 1 mod 4 would have to be odd, and 2 times a is always going to be even, so 2a is never equivalent to 1 mod 4. So there's nothing that is equivalent to 2 inverse mod 4. It simply doesn't exist. So once you write negative exponents modular a certain base, certain things might not exist. If, however, everything up here exists, then the two sides are always equal. Now, it is possible, now that we've got exponential notation, to define mod n logarithms as inverses of exponentials, but we're not actually going to use this notation nor that terminology. Fractional exponents can also be considered, like the 1/2 power being the square root, and we can try to figure out what that means, but we're going to postpone that discussion. It will come back later. Certain exponential expressions involving negative exponents might not exist, as we've seen, and when they do, we are only using integer exponents. Everything for our purposes here has got to be integers. The numbers, the exponents, the bases, everything. Now let's introduce some properties of these modular inverses. The first one we really want to take care of is, when do inverses exist? So we saw on the previous slide that it might not. Well, here's a basic theorem. If n is at least as large as 1, in other words, it's a legit base, and a is an integer, there is a solution to a times x equivalent to 1 mod n if and only if a and n are relatively prime. In other words, a has an inverse mod n if and only if it is relatively prime to n. This provides a very nice solution to the question, when do inverses exist? Exactly when the number is relatively prime to the base. So suppose there is such a solution. Then a times x is equivalent to 1 modulo n. In other words, n is a factor of ax minus 1. This is the definition of being equivalent mod n. Therefore, ax minus 1 is simply a multiple of n, and I move some terms around and I get ax minus kn is equal to n. Meaning there was a linear combination of a and n producing a 1. A got multiplied by the integer x, and n got multiplied by the integer negative k, and I added them together and I got out 1. By Bézout's identity, if a linear combination of a and n is equal to 1, then the GCD must be 1. So if there is an inverse of a mod n, if there is an x so that a times x is equivalent to 1 mod n, then a and n have to be relatively prime. Conversely, we can use Bézout's identity in the other way. If a and n are relatively prime, then it is definitely possible to find a linear combination of a and n that produces the GCD, which is 1. And you work backwards and you would get right here. Here's another theorem. If a is not equivalent to 1 mod n, and a is relatively prime to n, then a inverse is not equivalent to 1 mod n. This is a quick thing to prove. It's just a nice little initial observation. Suppose a inverse were equivalent to 1 mod n. Multiply both sides by a. On the left, you get a times a inverse, and on the right, you would get a times 1. But what is a times a inverse guaranteed to be equivalent to mod n? 1. If a times a inverse ever pops up, you know you have a 1. Then you would have a is equivalent to 1 mod n, contradicting our assumption that it wasn't. So a very quick little thing, all this says is, if a number didn't start out as 1, then its inverse is not 1 either. Having introduced modular inverses, we can actually now prove a tremendously important result that will come up all the time for the rest of the course. It is called Euler's theorem. If a and n are relatively prime, then a to the phi of n must be equivalent to 1 modulo n. Interesting, let's prove it. Suppose I start with a reduced residue system mod n. Well, a reduced residue system mod n must have exactly phi of n elements, so there they are, x1 through x phi of n. Since A was assumed to be relatively prime to n, I can multiply every element of a reduced residue system and remain a reduced residue system. So, having started with x1 through x phi of n as a reduced residue system, ax1 through ax phi of n is also a reduced residue system. Now, x1 is probably not equivalent to ax1, but x1 is drawn from an equivalence class of things relatively prime to n. So it must be equivalent to one of these things because this is a reduced residue system. So it has one element from each such equivalence class. So while x1 might not be equivalent to ax1, it is equivalent to something in this list. x2 is a representative of a residue class relatively prime to n. So something in this list must be relatively prime to it, and it has to be different from the one that was equivalent to x1. Since these two aren't equivalent to mod n, they can't be equivalent to the same thing in this list. So what I'm saying is, everything in the top reduced residue system is equivalent to exactly one thing mod n to something in the bottom one. It might not line up exactly vertically, but everything up here is equivalent to one thing down here and vice versa. Also, we have a reduced residue system. Everything in this top list is relatively prime to n, which means the product is also relatively prime to n. If I multiply together every element of this reduced residue system, the product p is still relatively prime to n. Now, since these two reduced residue systems have one element from the same collection of residue classes, the residue classes that are relatively prime to n, if I take this product, it will be equivalent mod n to taking a product of all of these. One by one, these are all equivalent to something in this list. So if I multiply all of these, it will be equivalent to multiplying all of these. Specifically, on the left, we get P, this product of the top reduced residue system. In this product on the right, I do get x1 times x2 and so forth, so I do get a P. But what else do I get? I get an extra factor of a for every term in the reduced residue system, and there were phi of n such terms. So I also can collect all of those together and call it a to the phi of n. So whatever this product p is, it's equivalent to a to the phi of n times p. And since we established p is relatively prime to n, we can cancel it out of a modular equivalence, giving us a to the phi of n is equivalent to 1 mod n. Thus concludes the proof of Euler's theorem. A to the phi of n is equivalent to 1 mod n, provided that a was relatively prime to n to begin with. This is very, very important, and we're going to use it a whole lot.